What's up, everybody? Today we are going to talk about something called time delay systems, and these are LTI systems, but there are time delays embedded in them. Here, first, we can see one such system. This is a given typical LTI time delay system, and we are going to LTI. We are going to derive or prove some LMI conditions that are required to prove the stability for those systems. And there is going to be two types of LMI conditions. First is called delay dependent, right? Delay dependent. And second is delay independent. However, these are the let me explain that. Wait a sec. First, delay dependent condition is I don't want to say if and only if, right? However, not that conservative as delay independent condition is. Okay, so and also now we are going to see delay dependent condition, not conservative, and also it is rather harder to derive, but of course once you derive that, you derive that. Okay, so time delay systems, LTI, LMI, and these are the time delay systems, also called sometimes infinite dimensional systems, because why? For example, let's consider system with only one state, right? And usually you would have a state. However, for those time delay systems, you have like the definition of state is kind of banded in, let's call it t and t minus t, right? So you can consider that as all of the points, which is like infinite, right, are kind of can be considered as state, right? And of course I'm being extremely vague right now, and we will focus on the LMI conditions now and not so worry about the mathematical aspects of the the general subjects. So let me get that out of the way. Okay, so let me delete all of this and let's begin. By the way, before that, quick reminder: Duan and you LMIs in control system design, right? And this is the book that I use for anything that is related to LMIs in control. Of course, Stephen Boyd has a really good book, but I need to admit something, that I am not in a position to understand that book, right? That book compared to the Duan and you is feels like more hardcore, right? Hopefully I will get in that situation where I understand that easier. Okay, so let's begin. Delay dependent condition. Here, this is given. This is the typical, like, for example, x dot equals ax plus bu, y equals cx plus du. Like, you write that immediately, right? You know that by heart, right? And this is the TDS version of that state space representation. Okay, and this is the general representation. I feel like, actually, you know what? I feel like I should first focus on delay independent condition because it's like really easier. Okay, let's move on that. Okay, Alright, where is that? The beginning of, alright. Delay independent. Okay. This is the typical state space representation for time delay systems. Okay. Here. We can see that. And also D, right? D is a positive number, and this D bar is the maximum delay, right? Okay. And the delay independent LMI condition. Okay, let's consider, let's take a step back. We have a system here, and we are only given A and AD, right? And the problem is this: find P and S symmetric matrices such that these given two constraints are satisfied. Okay, here A, AD, right? And P and S are the variables, decision variables that we need to determine, and they appear in linearly, right? Here, this is a easy LMI condition, LMI problem at this point. Okay, and now let's focus on why that is the case, why that theorem 4.8 correct LMI condition. Okay, first, as always, we need to determine a Lyapunov function. Okay, and this is the usual Lyapunov function that we would use, right, to prove LTI stability. However, there is one additional term as well, and that stems from the fact that this is time delay systems, right? And also, I mean, you realize that that's not the type of term that we are familiar with when we construct our Lyapunov functions, right? It's like a integral, right? Okay, and so the first step is this: the given Lyapunov function. By the way, this is a notation of aspect of the Lyapunov function, and let us obtain time derivative of Lyapunov function with respect to time. Again, by the way, we know that since P and S also, P is positive definite and S is positive definite semi-definite, and due to that reason, we know that is in fact positive definite. Okay, so now we need to find, or we need to determine if that the derivative of Lyapunov function is negative definite. Okay, so this is going to be similar to what we have done before. Okay, for example, these two terms, I mean, we are kind of familiar with that, right? Okay, and let us focus on the third term. Okay, here I just stated derivative of this term, right? Okay, and now we are looking at this, and maybe I should get back. Okay, here we can see ax plus ad x t minus d, right? Okay, so we just substitute that, right? Okay, here instead of that we just substituted this term. Okay, and same for this term, right? So far, each operation, each line of expression, right, equation, I constructed or produced these nodes such that it's really straightforward. Okay, so don't panic about it, I guess. And again, this is the same, no change over there, and this and this I am now looking at this and I feel like there is no additional operation between those two lines. Okay, however, this third expression is important. We need to kind of check that, and by using Leibniz integral formula, right? And this is that formula, and we kind of expand that third expression here. Let me zoom out a little. Okay, I mean, this is the formula, right? And here, for example, it says f t x, and however there is no x here. There is tau term available. Okay, and other than that, it is exactly the same. For example, this is b of t, this is a of t. Okay, and we just substitute each term here. This is ft, right? And instead of tau, we write t here. Maybe you can see that. Let me zoom over there. Wait a sec. Here, this is a one equation, and this one comes from the fact that this is a of t and this is b of t, and what is the derivative of a of t with respect to time? It's 1. Okay, and what is the derivative of b of t with respect to time? Again, it's 1. Here we can see the 1, right? And I especially explicitly show that. All right, and then here we substitute b of t, and we also substitute a of t. Okay, here this is a of t, and here this is b of t. Okay, and since this expression doesn't have t term, right, the derivative of that expression with respect to time is 0. So this whole expression is 0, and these are ones, right? And this term here, we get this, right? And this term minus here, t minus t. Okay, it's obvious at this point. And okay, so let's move on. We had these two terms, and now we have that term that came from the integral expression here. Let's look at that again. It comes from this third term, right? Okay, and now we have this, and again, a quick reminder, we need to prove that is in fact negative definite. Okay, so I'm looking at this here, we explain that line, and this is okay, term by term. Let's focus on each term. Okay, this is x transpose, and here there's transpose, right? X transpose A transpose P. Okay, and that term comes from this term. Okay, and PA, that term comes from this term, and also that term leads to that term. Okay, and here first this term comes from this term, okay, and maybe I should do something like that, and S term of course comes from that, and we have only one term, and that term comes from, or leads to that term, okay. And sorry, since we have that expression, let us arrange that. So we have x, right, and also we have x t minus t, right, two expressions, and it is a quadratic expression, right? It doesn't take much experience to realize that it's a quadratic expression, and so we need to put that in a quadratic form, okay. And for example, this term, right, leads to that entry, and here this term, this is like x and x, right, here, and also this term leads to that term, okay. And finally we have what do we have? We have a d transpose p, okay. It's straightforward. I mean, if somebody produced that note, right, and by spending lots of time of his, right, and it looks straightforward, okay. However, they don't explicitly they don't give that on their, people don't straightforwardly prove even the easiest theorems. So you're welcome. And now we need this term to be negative definite, okay. However, since this is quadratic term, we have that matrix, right, and this matrix must be negative definite, right. And since from the Lyapunov function there was a p, right, and that p must be positive definite, this is our first condition, and this is the derivative condition, derivative v being negative condition. So at the end we have this condition. Just find a p and s such that these two given conditions hold, and then we prove that the given time delay system, linear time delay system, is stable, okay. And that's easy, okay, that's easy. And now let us focus on one more thing, and this is kind of conservative condition. What I'm trying to say is that we can have a system, right, we use let us say LMI 1, right, this is LMI 1 technique, and LMI can say us, or we are not able to find a p and s, and you can think, hey, maybe that is not stable. However, now we are going to see LMI 2, right, delay dependent, this was delay independent. However, LMI 2 will be delay dependent, and that delay dependent condition will be much more or much less conservative, right, condition. So there are systems where using only LMI 1 we can get the conclusion, hey, that is not stable. However, by using LMI 2, yeah, that is stable in fact. And these are sufficient conditions, by the way, right? If they hold, that means the system really stable. However, if they don't hold, we cannot actually say systems are unstable. And again, sorry, S implies P, right? Here, sufficient condition, and here, this, what, sorry, wait a sec, sufficient condition and necessary condition, right? So those LMI conditions are, for example, LMI, if they hold, that implies stability, right? Okay. However, stability doesn't imply that condition. Okay, just wanted to point it out. These are all sufficient conditions. And we often strive for less conservative conditions, all right? So let us focus on the delay dependent condition, okay? Because the first LMI that we checked was something that doesn't have much regard for the delay term, okay? We didn't see a D term in that expression, and now we are going to see that here, here, here. We just first written x dot term here in that fashion, and now I'm looking at my clock. Okay, everything all right. And now I mean, there is one derivation, right? From here to here. This is straightforward. However, you may think that is not, well, okay, just this part is not straightforward, right? So let us not think about AD, right? And just this. To be honest with you, I couldn't get from this to this. However, I can get from this line to the linear term, I guess. And this is the fundamental of theorem of calculus, right? And you just use S0 and x t plus s minus d. Okay, let's substitute them. X, okay, minus x t plus or t minus d, right? Just a fundamental theorem of calculus. All right, that was messy over there. Okay, let's now. So we have this expression as x dots, okay. And now let me zoom out. The theorem is this. The theorem here. Just find, right? Yeah, that's exactly the theorem here. For a given dm, dm is maximum delay, okay, for a given dm, find x and beta x. Maybe I should better, these are the terms that we need to find, right? Beta x here, beta, right? And they appear linear, right, in each entry. And this, let's check what phi of x is here again. that's also linear. So that's totally a LMI that we can handle, right? All right. And now let's prove this theorem. Again, that's also a sufficient condition, but less conservative one. Okay. Here, this is going to be messy, by the way. Okay, so heads up. And this is the Lyapunov function, right? Again, the first term is something that we are familiar with. However, there are two other terms, and I feel like if that is your first time seeing them, you're like, wow, what are those? It's really complicated. And they're complicated, and I called them term 1, term 2, and term 3. Okay, and just consider this. Someone came up with that expression. I mean, I imagine they must have put in a lot of work to that, right? And this expression, since it's like quadratic, right? Positive definite is given, all right? However, now we need to find the time derivative of that expression to be negative definite. We need to determine that, right? And even taking the time derivative of that expression is going to be really messy, right? And will look complicated. And okay, so let's begin. We need to take the time derivative of that expression. All right. Here we have t1, t2, and t3, right? Okay. Wow, that looks incredibly small. I'm kind of sorry for that. So here, time derivative of that, and since we have that, take the time derivative of each expression. All right. Let us focus on the first expression here, and this is something that we are familiar with, at least, right? Okay. However, x dot expression is not that simple, right? So we just substituted x dot expression, and this is it, right? And this is x dot again, and we just, since the integral operation is linear, we just kind of decompose that, right? So this expression and this expression, they come from this term. Okay, here the same thing. These are like symmetric. And now I label the terms to make things a lot easier, and I called red, green, and blue terms, right? And okay, so red term, t1 red, time derivative is this term. Here, why that is the case? Why that is the case? I mean, just look at that, right? And here we have transpose that comes from that expression here, just, right? And also we have that expression also comes from that. So at least we got that red term down, all right, or arrange, right? So let's focus on the green term, all right? Here, just this term, again px, right? And minus ad, okay? Okay, so we just gather the green terms is what happened. However, there is something that we need to keep that in mind. V of x is scalar, right? We know that. And v dot of x also scalar, right? And we know that this whole term is scalar, and in addition to that, this term is scalar and this term is scalar. So, and since there's kind of a symmetry between, we can consider that, right? There's some symmetry. We can see that pattern, right? And this expression is if we take the transpose of that expression, we get this expression, right? And two expressions are themselves scalar, so we can take the transpose of that, right? And since it's scalar, it wouldn't be a problem, and it would be a legit operation. And so we can write that as 2. Okay, let me tell A transpose plus A, right? If you have that expression and you know that A is scalar, you would directly write 2A, right? Okay, this is as basic as that example. So here we just take the transpose of that, or rather take the, this is the transposed term. Okay, we just take the transpose of that here and obtain that, and then we get that expression. Okay, we have red, green and blue. 2 of them are done, and now we are going to focus on the blue one, right? The blue term. And here that was the blue term. I understand there are lots of expressions, and that's why you can download this PDF file that I produce, right? And from the GitHub link down in the description section below, right? And okay, this is the blue term, and again it's scalar, right? The same thing, same, right, way of doing things. And we just transpose that term and obtain that term, right? And after that we obtain this. It's like the same. Okay, and so all right, so far v equals t1 plus t2 plus t3, right? And we need to find v dots. First t1 dots, we are done with this term, and now we are going to focus on t2 term, and after that t3, right? And again we are just taking the time derivative of a given Lyapunov, however complicated it is, and complicated Lyapunov function, and even taking the time derivative of that looks complicated, right? Okay, and imagine, I mean, we are just analyzing it. Analyzing is like infinitely easier compared to synthesis, right? Okay, we are just analyzing if a given Lyapunov function is indeed can be used to prove stability. And imagine having to come up with a Lyapunov function, right? Okay, so this is the term 2, and we need to take the time derivative of that expression. And by the way, in time delay system, the Leibniz integral formula, right, it always appears. And so first of all, let's focus on this expression, and only this expression have t term, and here we can see the time term, right? Other expressions, they don't have that, so we can just get that derivative operator here in that position. Okay, and as soon as you have that type of expression, your brain sounds like, hey, Leibniz integral formula. It would be a really awkward or annoying alarm, right, in your brain that should go off immediately. when you see that. And okay, so let's remember what that was. First of all, here Leibniz integral formula, right? And this is the scalar case, right? And this is just a formula, right? And this is the one that we need to use right now. Here we have three terms, 1, 2, and 3. So we are just going to substitute that. Here, let's check that, for example. Here we are focusing on this expression, okay? Here t derivative operator. Here this is b of t, and this is a of t, and this is indeed, and let me call that theta, right? This is f t theta. Okay. However, that f doesn't have t in it, right? And that's why that expression will be 0, and that whole expression will disappear. So we will be looking at those two terms, and since it says derivative of b, right, and since it's like t here, t, it's 1, and this is again t plus s, and the derivative of that again 1. So this might be the most boring video I made, probably. Okay, so we just substituted that. Here we can see that, and also here like this one, right? Okay, so you can see the parallel. These terms are indeed parallel, right? Here, okay, here, this one, and this is 1, right? Okay, and since this is 0, we only have these two terms, and we substituted t instead of theta, and here in that expression we substituted t plus s instead of for theta, right? So let me delete all those, and at the end we have that. And again we need to, by the way, we determine this expression, and now we have some scalar and also integral, right? So we are not done, is what I'm saying. Here this was the expression, and we just determine those two factors, right? And we just, I guess, decompose that, expand that, and then since that expression doesn't have s as a variable, right, we can get that out of the integral, and we have at this moment 0 minus d 1 times d of s, and that is, sorry, not d, s 0 minus d, and this is 0 minus d, and that's 0 plus d, and that's d, right? So that d term comes from that derivation. Okay, here that d term, and this is the term, and also since that expression has s in it, we just leave it as is, right? And so this is the derivative of the second t2 term. Okay, and the same logic will apply for the t3 term. However, I am not going to go into the details of the Leibniz or implementation of the Leibniz rule, right? on that integral expression. And here the same expression, again very similar expression, right? Again, and now we need to determine that, expand that, and again by using Leibniz integral formula, right? We have, what do we have? We have this, right? And again, this expression doesn't have t in it, right? So that kind of makes things a little more easier. And maybe, okay, so here, and by we use Leibniz rule and we get that, and again we decompose that, right? And the final expression is this line. Okay, so we have t1, t2, and t3. We've taken the time derivative of that, and I guess I written one more. No. I also, yeah, make things simpler. I simplified that expression. Okay, so as a result of this, we have, and this was the first expression, right? Here, and explicitly, let me fit that in the screen, and explicitly we have that, right? So at this moment, since we know v is positive, we need to determine this whole complete expression is negative definite. Okay, so we need to make some type of simplifications, right? Some factors need to cancel each other out and stuff, right? And then we hope to get something like quadratic probably, and like x transpose z x, right? And that z matrix must be negative definite. That kind of mentality we should have. So first of all, and these two expressions are same by the way, and I just denoted these two terms with red color, right? And now we need to focus on these two terms. Okay, there's a really interesting thing will take place here. First, let's check this expression, right? Okay, and we have lemma 2.1. Even in the book it says lemma 2.1 by using that. However, it doesn't use only lemma 2.1. It's also use a couple of things, right? And so if you study from that book, and also any book by the way, right? I'm not excluding, right, any book. And if you study from that book, you will feel like, hey, what is wrong with me? Why can I understand or derive that expression? It says from lemma 2.1, but it doesn't say actually from by using only lemma 2.1. Of course it used lemma 2.1, but if it I mean it used like a couple of things, couple of lemmas and corollaries as well, right? And for some reason they like to omit that things and make students feel like they're not fit for the job, I guess. Okay, and so before I rant about that, here this is the lemma, and we are going to use that. However, you can, I mean, if you want to have that expression for that term, let's focus on this x plus y, right? And if we square that term, we will have that, right? And this is SOS term, right? And or this only square term, it can't be negative, right? And let's expand that, x plus y plus x square plus y square plus 2xy, again that greater than 0, and let's carry that over to that location, and x squared plus y squared, it is greater than and equals to 2xy. Alright, and this is the scalar version of that expression. Okay, so okay, let us focus on, yeah. So we have okay, check this, x, f, and y, right? And we need to determine what term corresponds to x, f, and also y. Okay, here we just written that expression such that we have x transpose f and y, and since they cancel each other out, right? However, I written them in that way because of course there's a great reason for that, and in addition to that, we have also delta, and delta is some positive number, right? And I am really hoping that you don't have hard time seeing that. Okay, maybe you can check the PDF on another screen and you can follow along with that. Okay, so we just written each term. Okay, so, and beta is the delta here, and we just carry that d over to that location. Okay, this is actually not hard. However, since there are like tons of terms, it makes seeing the pattern really harder. And now we have this, and this expression is, yeah, it kind of made me waste my like 4 hours or something yesterday to understand or to come up with the logical explanation why the, okay, now I'm going to explain that. So we have that, right? We have that. However, we have also something called Cauchy-Schwarz, right? And let me delete that and let me write that here, Cauchy-Schwarz. So we have some integral, right? Definite integral, by the way, and we squared that. If you have that term, right? If you have that term, you can find an upper bound, and upper bound is given by this term. So, do we have that term? Do we have the square of a given definite integral? And yes, it doesn't say square, but it says transpose time itself, and it's in matrix language, it is square, right? So what is b minus a here? This is a, sorry, this is b and this is a, right? And b minus a is d because of that. Okay, yeah, really worst video, by the way. Anyway, however, the subject is like the worst. So, all right, let's focus on that. Here, okay, and we just square that basically, right? And since we have 1 over d, we have 1 over d square, and then we have, just get that out of the integral, right? And we have this expression here. Okay, so we have a upper bound. Okay, so let's recall what we have done. We have that term and we upper bounded that by that term. However, these expressions, these two expressions, highlighted with color, red color, right? So basically, they are upper bounded by this term. So let's imagine we get this term over to that location, over to that side, right? And we have this here. Okay, this term and this term. All right, and now that was important. Why? Because we have 4 integral terms in our v dot expression, and we cancelled, we kind of eliminated 2 of them, and we kind of, I mean, since integral terms are like harder, right? We like to upper bound them by non-integral terms, basically, right? Because the non-integral terms are easier to handle, right? And again, we need to find a, first we upper bound that v dot expression, right? And then we need to prove that upper bound is negative definite, and since we are going to, and then we will conclude that since the upper bound is negative definite, v dot is negative definite, and hence the stability. Okay, so all right, we have v dot, and those 2 red expressions are the expressions that we dealt with before, and instead of them we are going to type this term, right? And now again we have 2 other integral terms here, and lucky for us there is a similar technique, right, that can be applied. However, I will not apply that. That's Cauchy-Schwarz inequality, and also I guess the quadratic. I don't know the correct expression, by the way. Lemma 2.1, right? This is it. We use Cauchy. We use that lemma, and also we use, where is that? Yeah, we use this Cauchy-Schwarz. Okay. Again, by using that, we have it's really, okay, it's really long term. Okay, again we have that type of inequality, and we will substitute that term instead of those integral terms. All right, so yeah, that's going to be longer, but in a way simpler. So finally we have v as v dot this expression, and we know what this expression, right? And here this is okay, and what was the other? Beta d. Okay, let me check that. AD, right? A sub d. Okay, I'm looking at this right now. Okay, and this one, right? And we already had these expressions. So, and since you kind of realize that each expressions are sandwiched between x transpose and x, right? We are going to correct them. And before doing that, check this expression and this expression, right? They kind of cancel each other out, and we have that. Okay, and sorry, wait a sec, I didn't do that. I'm looking at this, and we only have okay, this comes from that, and yeah, this and this, okay, leads to that term, and this expression again leads to that term, and that's stays the same. So wait a sec. Okay, now let us look at that. We just gather the terms, right, here at this moment, and D here, D is upper bounded by D max. I call it dm because max would be longer and the expression is already long. So that expression is also upper bounded by the dm version of that, right? Let's say that. And also let's put it in a matrix form, okay? And here we have that. So this matrix must be negative definite, right? Okay. By the way, we are very close, by the way. And here that must be negative definite. And we need to pre and post multiply the left hand side of that inequality, right? And after doing that, we also denote x, right, as P inverse. So here you can see that. I guess that is the same, right? Okay, so here this is the expression, and we just pre and post multiply by x, right, here. And whenever we see x and p together, they cancel each other out. So here this is 1, this is 2, and this is scalar, and this is again x and p together, right? They appear together, so they cancel each other out. And then after all those cancellations, we have that expression. And since it's like very long, right, and we just denoted phi of x, and this is the only expression where x appears kind of linearly or affine manner, right? Other expressions x appear quadratically, so that's why we excluded that terms to indicate something called phi of x, okay? And now we have this, and again after really, I mean, it looks simple if you have that document, right? However, it's like in each step you're like, okay, it makes sense, but why, right? It's like, hey, go along with me, and in like 10 or maybe 20, maybe 30 steps later, you are going to see why I do this. It always like something like that, okay? And here we can see the equalities, right? And here also we can see that. And you are like, why would you write that in that form? Of course there is a reason for that. And so trust the equation here. Just let us focus on the second and the third term first of all, right? Here, and they are quadratic, right? They are quadratic expressions, and that's why we can write them in this form. It's like directly you can write them, right? Okay. For example, it doesn't take much intelligence from taking that expression and put it in like x transpose ax kind of form, right? Okay. Each manipulation is like really simple. However, yeah, those like incredibly small expressions, like 10 of them, maybe 20 of them, they result in like really very complicated or significant result, significant LMI condition that we then, and it simplifies things a lot easier, right? If we have LMI condition, we can just directly use ULMIP or something like that, right? To obtain the variables and to prove stability. Okay. So again, this is the term, and just multiply minus and again minus with that. For example, this, I mean, even that, we just put -1 times -1, and then we move -1 to that matrix, and we multiplied each entry with that -1, right? I mean, usually these are the kind of things that you would, hey, why would you do that? Okay. And for example, this is matrix, right? And this is the inverse of that matrix. Okay. And again, recall A, B, since this is diagonal, right? The inverse of that is A inverse and B inverse, right? This is the same situation going on. Okay. So yeah, I mean, if you are kind of expert on LMI, especially inequalities, this is the term that you're like, hey, it's like sure complement. I don't know maybe what it is exactly. However, it is typical sure complement, right? Okay, what was sure complement? For example, if you have that type of condition, you can write that condition such that this, and this expression is the sure complement of A11. Okay. Again, you can also write A22, right? And by this term, and that term is the sure complement of A22. Okay. And we will use that term. So we have that kind of term. Okay. Here, please notice the pattern, right? It's all about patterns. And here I also expressly written that we have this, right? And we are going to call A1 phi and A2 that's transpose vector, and A22 the vector, and A22 is the matrix. And so let us see, right? And that comes from this expression, by the way. Okay. Since we have that, we can also write this, and this is a lot simpler, right? Because this expression is like quadratic, right? It's not linear, and we like to have linear terms, and that's why sure complement is that type of technique is like really makes things easier, right? So finally, the delay dependent LMI condition is given by this, and let's write that in one last form for a given dm, and dm is the maximum delay. Okay. And you have also uncertainty in the delay. For example, your delay it can be between 0 and 1. right? Your system is operating, and the delay, that delay operator, it is not like always 0.5 seconds delaying your state, right? It's delaying between, I mean, even the delay operator kind of changes, right? And it's really complicated. I mean, it's, to me, it's amazing that we have that type of LMI condition to prove that. Although it's sufficient, of course, there is some, by nature, some conservatism in that, and it's sufficient condition. However, I mean, it's amazing we have that type of LMI condition. I mean, this is, by using YOMIP, you can just directly prove the stability, right? And okay, I guess that's it. So thanks for watching, and remember to subscribe.